I'm Nigel Forrester from Current Technologies. I am the technical marketing manager there. And as Jerry was just saying, he always challenges us to try and be topical. So my title of my presentation today is The Dark Powers on Intel Processor Boards. So I'm going to switch gears a little bit. There's a couple of technical things we're going to talk about. Hopefully they'll be sort of interesting or semi-interesting to some people, but not too product oriented, and I don't have many words on my slides. First of all, very little bit of background about Intel processor boards. So thinking about a 3U VPX form factor power envelope, it's been a little bit of a change over the last year. So a couple of boards we introduced, as many other vendors here. The one on the screen is the sort of new style, I suppose, within this form factor. So more of a server-orientated board, multi-core CPUs, up to 16 cores within a single board, lots of memory, but no GPUs. And that is really a bit of a change from perhaps the previous high-end processor board that we've been supplying, where we have, in this case, up to 4 CPU cores, but multiple GPUs. So there's sort of a paradigm between those two types of boards, which we'll touch on through the presentation. And as you can really sort of tell, there's not just one Intel single board computer anymore. There's lots of different things you can do with these devices, and hopefully I'll introduce some of those things as we go along. So one thing that I was thinking about before the presentation was, sort of do all these clever things with Intel boards. Intel come and talk to us every 3 months, and they always introduce some new marketing phrase, and they've got a whole gamut of those. And I'm sort of thinking about, that's me with my bewildered face on, sort of how do these really relate to the customer, and are they relevant to some of the embedded people that we deal with? Is there a good use we can put to them? And I'm thinking that there probably are. And I've actually chosen 3 of those technologies. These are the 3 things that I'm talking about. So I'm sure everybody will here know what TFXNI stands for. Just in case anybody doesn't, I'll explain that a little bit. I'm going to talk a little bit about resource and cache allocation. And I'm then going to switch gears a little bit more and see if I can show you a good use for some of those GPU cores that we have on the traditional mobile workstation type products. So TFXNI is a section of new instructions. They're transactional synchronization extensions, a very catchy title. And this is really an introduction that Intel has made over the last couple of years to enable their processor engines to work better for high-performance computing workloads. So several speakers yesterday were mentioning things like cloud computing, mist computing, fog computing, edge server type applications, where often processing, they're required to do transactional processing. Maybe that's sort of assembling lots of disparate bits of information and coming up with a result. Maybe that's image analysis. And in those sorts of transactional applications, you've got multiple threads running. And so these new instructions effectively optimistically execute those transactions with the expectation that when they put the results back together or they're using common memory, that the transaction that needs to be executed first will have executed first. And if that doesn't happen, then there's a hardware rollback feature so that they can go back and actually reassemble all the memory in the right order. So what they've found is that it's a really easy thing to implement from a user point of view. And for your transactional processes, you can actually get up to about 40% benefit, effectively for very little effort. So it's a good example of where, for those types of applications where Intel has been traditionally, if you're doing lots of transactional processing, DSP, FPGA type processing, then there's always a better way to do it. But quite often the Intel will provide you a good enough solution, and all the time they're giving you a little bit better way to do that. And the interesting fact for me which I didn't realize until I started to look into this, was that this TFXNI set of instructions is actually not just available on the big Xeon server type processors, but actually available on the mobile workstation processors, so pretty much across a reasonable number of our products. So switching gears for my next dark power, I'll give you a little bit of a background to that. So it's really talking about resource allocation strategies. And if I think back to the old days, it was pretty easy. You had a single core processor, you had an operating system, and you had an application that was a single-threaded application. It was very simple to allocate your resources in the right way. And then over time, with modern operating systems like Linux and Windows, multi-core processors, they're now sophisticated so that if you've got a 4-core processor, that operating system will probably schedule your application to run across all of the available resources without you doing anything or knowing about it. And then as an added level of complexity or usability, depending on how you look at it, that in the server space, virtualization enables you to run multiple separate virtual machines on a single processor. And that actually has quite a nice side feature that when you set up a virtual machine, usually you can actually allocate a specified number of, or maximum amount of number of cores or memory to that particular virtual machine, but you can't get down to a further granularity than that. And so one of the observations that we've seen in the picture at the bottom is that on most of these processors, they've got multiple cores, they've got various different level 1, level 2 caches, but then they have a level 3 cache, which is shared, or last level cache, which is shared between all of those cores. And that's one of the things that you typically can't control or allocate on an Intel processor. A couple of observations about virtualization that I think might be relevant because it's still not widely used in the embedded space, although we've seen much more interest in it recently. Whereas if you compare that to the data center space, virtualization is a very mature technology, widely used. And in fact, it's got so widely used that there are now some people in the data center, because the costs are pretty much a wash, virtualization licenses are quite expensive, that I've heard this term physicalization start to come into play, where some people are actually, if they're not worried about size, they're not worried about space or power consumption, they can buy 6 boxes, stack them on top of each other. They don't need to worry about creating virtual machines. But think about this in the embedded space. How many presenters have talked about swap-C? Pretty much everybody across the board. It's very important. We are space constraint, weight constraint, power constraint. So those being able to set up virtual machines on one blade is a very nice feature and something that gives a lot of scope. So that's really what we're going to talk about in the next slide. So this is my dark power number 2, and it's a thing called cache monitoring technology. So think about that shared layer 3, level 3 cache. You can actually now go and investigate how that's being used. Now I've got a simple example in the slide with a low priority and a high priority task. The low priority is in the orange color, the high priority is in the green color. And in the last level cache, you can see there's sort of a mix, roughly shared equal between the 2 priority tasks. So you can now actually go and investigate how that cache is being allocated. And you can see in this instance, this sort of low priority task is being a bit of a nuisance, and it's actually called a noisy neighbor. So it's like having somebody sitting next to you chattering away. It's sort of distracting the high priority task here. So my dark power 2.5 is that not only can you look at the cache monitoring, you can actually go and allocate it yourself within some bounds. So here I've got a different picture. The low priority noisy neighbor task is squeezed a bit, he's quietened down, whereas the high priority task is actually enabled to use more of that cache. And what that does in terms of a customer is it improves the determinism of the solution. I've got a couple of examples. These are from some information, some data from Wind River. We have a white paper if anybody's interested. I can give you some more details about this. So the first picture here is without the cache allocation. And this particular application was running the noisy neighbor caused the interrupt latency for the high priority task to vary between 7 and 10 microseconds. With the cache allocation technology, that noisy neighbor gets quietened down, the latency is totally stable at 7 microseconds. So not only can it improve latency, it can improve throughput. So I've got another example from Wind River, where they're running a packet processing application with a classification and scheduling stage. They had 2 10 gig Ethernet inputs into this system, and they found that running a single virtual machine, they could actually get 11 million packets per second out of their system. But once they introduced a noisy neighbor into that, the throughput dramatically dropped down to 4 million packets per second. So significant change there in the system performance, system throughput. But if they quieten down the noisy neighbor by reallocating the cache towards the primary virtual machine, then they could actually re-establish 11 million packets per second throughput. So think about our embedded type of solutions. Determinism, latency, consistency are very key technology providers or technology things that our customers are often looking for. So we can give you some more tools there. So that's my dark power number 2. My dark power number 3, switching gears again completely, is looking towards those GPUs. So this is a picture of a 4-core mobile chip, courtesy of Intel. This is actually a 4th generation Haswell processor that we and many other vendors widely use across many of our products. And you can see that there's the 4-core CPUs sort of in the middle, top of the picture, and then there's the graphics engines towards the left. And so what we've been looking at, using a free Media Server Studio software development kit from Intel, is how can you as a customer make use of those GPUs? Because whilst some applications for embedded use high graphical capability, and I think we had some examples yesterday of display systems where there were real-time display capabilities. The reality is that many customers in the embedded space either only use the display for setup, maybe some pretty static displays, and in many cases have no displays connected whatsoever. So you've got these GPUs sitting there, can you actually make use of them? And what we've found by doing several benchmarks, this particular example I'm giving is on a fairly decent sized matrix multiplication. We've got many other examples that we've looked at, is that using standard OpenCL, and OpenCL, if you've not come across it, is a programming paradigm that enables effectively heterogeneous computing. So it basically uses your compute resources, and it's very convenient. You can actually set it to use only the CPU resources, or you can switch it so that it uses both the CPU and GPU resources. So in this case, if you switch on the GPUs, you get a small benefit in terms of the reduction in time. That actually is amplified a bit if you use the same matrix multiplication, but use the optimized algorithms that, again, you get as part of this Media Server Studio SDK. The axes on those graphs, you should note, there's a 10-to-1 difference. So the bars are 10 times smaller, really, on the bottom size. And you can see that, effectively, you're getting something for nothing here. If you want a performance improvement in your system, and you can actually make use of optimized OpenCL code, why not? If you're not using those GPUs for anything else. So there's a couple of other just data points that you might want to think about. First of all, we also did some comparisons with both completely standard C code. Not surprisingly, that comes out extremely poorly, much higher time to deliver. But we also compared a reasonably optimized maths library, which runs only on the CPU. And the figures for the maths library are roughly comparable with the optimized OpenCL CPU only. They're slightly better in general, but by using those GPU resources, you can significantly improve your performance compared to an optimized maths library. So that's perhaps something worth thinking about. So there are my 3 dark powers. I've got one more slide to end on. Just about got time before I'm ushered off the stage. So I thought it might be just a little bit of fun to go back and look at how far we've come, because we're always looking into the future here. And unfortunately, I could only find in my archives one of our products that dated back to 1990. So there's a few more lurking prior to this. And this is a multibus 2 board that we delivered. It's actually a communications board. It had, I think, 8 RS-232 channels, which was quite good for its day. 386 processor, 20 megahertz. It had a massive 4 megabytes of DRAM. It actually had 4 megabytes of EEPROM, but that wasn't really sort of solid state storage. That was really just for our firmware purposes. And I thought this was a really interesting fact. It actually had built-in self-test. Well, we're still improving that today. We still deliver that on our VME, VPX cards. But we've now, had 25 years to perfect that, 30 years, I guess. So if I compared that to one of our modern processors based on the just released Intel known as Kaby Lake chipset, we're talking about a huge improvement in performance. But even more so, if you look at the difference in processor memory, storage, really because there wasn't no storage on these boards, we had separate storage. It sort of tells quite an interesting picture. So sometimes we get a bit, fixed on where we are today and the little changes between this year and last year. But if you look at the trend, there's it's quite an amazing sort of times that we've lived through. And actually, there's probably no sign that that's coming to an end. So interesting times to come. So with that, I'll say thanks very much.